And we're back with another episode of Open Analysis Live. I know it's been a little while since we posted a video, but we're going to do our best to try and get one of these out a week. I say that, and I'm actually going to end up going on vacation for the rest of the month. So there's probably no videos until May, but hopefully once May hits, we'll be able to get back on a schedule of like one video a week. You guys have sent in a lot of really awesome ideas. We have a couple samples to look at and a couple really good ideas. We are listening. I know some of you are messaging back and forth, so we will put out some more good videos, again, probably starting in May, but for right now, this will be the last one until the end of the month. And today we're going to talk about domain generation algorithms and how to reverse engineer them. So what we're going to do is we're going to look at sort of an overview of what is a DGA, and then how to find one in a binary. So let's say you open the binary, like what to look for, and then how to reverse engineer it. So how to find out what the random number generator is. Usually there are common random number generation algorithms that you can just find online. How to replicate that in Python, and then finally how to put it all together to build your own client to basically generate the same domains. So this is obviously very useful if you want to sort of get ahead of malware. If they're using a DGA to sort of hide and hop to new domains every day or so, you can just build your own client, generate the domains for the future, and then you've sort of generated a blacklist of domains going forward into the future. So that's kind of why you might want to look at a DGA, and again, we're going to show you today sort of how to do this. Now, this is a bit more advanced than the other tutorials that we've been doing. You do have to know a bit of assembly, and we're expecting that you're going to be a little bit more experienced. We're not going to go through how to unpack the samples today, so you can look at some of the other videos we've done on unpacking. We're just going to look at, once you actually have the payload, how to locate the DGA, identify what it is, and then how to replicate it in Python. So before we dive into the actual code, let's talk about domain generation algorithms and what they look like. So basically, with a DGA, what you want to do is you want to have a random number generator. So there's just an algorithm that's going to generate a new number in a sequence based on an iteration through the algorithm. So like I said before, there are lots of common random number generation algorithms out there. It's very common to just see these being used as the base for a domain generation algorithm. So to feed that random number generator, you're going to need a seed. So this is a value which starts the series of numbers that will be generated. Different approaches, and we'll talk about this in a second, different approaches use different things for seeds. And this is a very important part of the DGA, is finding out what the seeds are. Once the random numbers have been generated, these are then transformed or modified through some sort of another algorithm and turned into either the characters or the words that make up the domain that's being generated. So two common examples that we see, the two most common DGAs that we see, are either where they use the random numbers, they modify them to fit into the ASCII character space, so into the char space, so lowercase letters and numbers, or lowercase letters, however it may be. And so for each random number, they will compress it into that char space. And for each random number, that will generate one character in the domain for however long the domain is. So that's a very simple way to generate a domain. And then based on the seed, you can predict what those domains are going to be. Another method that is popular with a lot of Zeus variants, the Gauzy variants, all the iterations of that leaked source code have used some variation of this, where instead of using the random numbers, instead of compressing them down into the character space, they use them to locate a word in a text document. So for each random number, it will be the offset to a word in a text document. And if you guys, if there's any like malware veterans in here watching this, you'll probably remember the Declaration of Independence was used by, I think one of the original modified Zeus Trojans was using this as a DGA. So basically what they would do is they would download the Declaration of Independence, which is a static file. I mean, all the words are always going to be the same. They transform those words, like they remove the punctuation, remove uppercase, et cetera, until they were words that could be turned into domain names. And then they use the random number generator to generate the offsets to which word they were going to use for the domain. So basically, those are like the two most common types that I've seen, at least for DGAs. But the important thing is that we break down that whole algorithm into the components that we see here on the screen. So we need the seed, we need the random number generation algorithm, and we need the modifier that turns that random number into either a character or a word that will then be used in the domain. So that's basically DGAs in a nutshell. And the sample that I'm using today, let's pop over here. So the sample I'm using today is Ramnit. I misspelled that, but it's RAMNIT. The DGA for this has already been reverse engineered. I simply chose it because this is a current sample. It came out a couple weeks ago, so it's still current, still relevant. I chose it because the seed in this one, and we'll get to this, and once we start reverse engineering it, the seed has not been publicly picked up. So I noticed that some AV companies have this seed, and they've actually sinkholed the DGAs, but I didn't find it on any blogs or anything. So I thought it might be interesting to do this. And lastly, this sample is pretty straightforward. So like the actual domain generation algorithm is very straightforward, and it lends itself very well to this tutorial so that you guys can sort of see each component separately. I think it's a good example. So just to take you through how I got the payload very quickly. Again, I'm not going to show any unpacking, but I just want to talk about it in case you guys want to replicate the steps. So there will be links in the description below the video for the links to the samples, so you can download them, links to the malware runs, so you can take a look at how they were run in the sandbox, and any sort of extra notes that I think are relevant are all going to be in the description below. So the sample that I started out with, like I said, this was pulled a week or two ago, or a couple of weeks ago. This was being delivered through via a phishing campaign. It's one of these silly like installer packers. So if we take a look here, you can see it's like one of these like installer type packers, which I really I don't spend a lot of time to like actually reverse engineer these things. What I do is I just let them install, and then I grab the installed components. So when we can see, if we look at the drop files, we can see they drop this file here. We can see the MD5 for it. The reason why I was particularly drawn to this is because if we look through the API calls, which I won't do right now, but we can see that this is actually being run. So I suspected that this might be actually the extracted payload. So then I grabbed that and I just added the .exe extension, and I ran it in the sandbox again. So let's take a look at the network. We can see it's calling out to what look like some domain generated algorithm DGAs. So this looks like a good sample to start with. We're going to try and figure out how these domains here were generated. And it's important because this sample is also packed. Obviously, it's multi-stage packer. I'm just going to talk really quickly about how I extracted this, just again in case you want to follow the process yourself at home. So if we look at the behavioral analysis for this, we can see that when it's run, it starts another sample that we can see from the API trace. I think I can actually, no, I don't think it's shown here. I don't think malware catches it, but when I ran it in our own sandbox, you can see that this sample is actually written to disk from this sample before it started. So there might be some sort of injection here or something. I don't really care too much because I can see at the end it's starting these SVC host processes. So immediately we can say, okay, well, it's probably injecting into SVC host. So all we have to do is look at those processes and see whether they've been hollowed out. And indeed they are hollowed out. And the sample that I'm going to be looking at today, it injects two different components which talk to each other. That's what Ramnit does. And the component I'm going to be looking at is injected into one of these SVC hosts. It's a DLL, and it's the DLL that has the algorithms for network communication. So that's the one that we want. How do I know this? Well, unfortunately, I can't show you again, because if we look here, MALWARE, I believe it's like a userland DLL. They don't have the kernel one set up for malware.com yet, so they're not able to really trace inside these processes that have been started up. But we have like an extractor script that we run that was able to just extract the hollowed process, no problem. So that's what you're going to be looking at today. Is you're going to be looking at the DLL that was injected into one of these SVC host processes. And we're going to be, just to recap, we're going to be attempting to build the algorithm that is generating all of these domains here. You can see also, just before we start, it looks like that's not a DGA domain, and Google obviously is not a DGA domain. So you can see that there's probably going to be some other network traffic in here. I don't really, in this tutorial, I'm not going to dig into it. Again, I only want to focus on the DGA. But it might be interesting if you guys want to go and check it out. I think if I was a betting man, I would bet that this is probably a check to see whether the internet is working on the host that's infected. But I don't really know. I didn't look at it. Again, the focus today is on the DGA itself. Okay, so let's go jump over to our IDA instance where we have this DLL already loaded up. So you can see if we go to exports here, you can see it is a DLL. We're in the entry point here. Now, the first thing we want to do, since we know that this is, or at least we strongly suspect that there is a DGA in here because of that network traffic we saw in the sandbox, what we want to do is we want to locate the communication functions, so all the functions that are responsible for setting up network communication. And then from there, we want to find out where the host names come from for that network communication. So a good place to start is with the imports, because based on that, we can just look for the functions that require a host name. And from there, we can kind of work backwards and hopefully identify where the DGA is. And there's another technique, which I'll show you in just a second. It works just as well, where we look for the TLD string. But let's do the backtracing of the network functions first, or the network APIs. So here we can see the libraries. Here's our network library, and here we have get host by name. So I think that's probably a good place for us to start. Let's go and see if we can see where get host by name is used. So it's used in two different functions. So we're gonna have to do a bit of digging. Let's take a look here in this function first. So one thing I want to note about when you're reverse engineering algorithms from binaries, so if you're trying to actually replicate the algorithm, say in Python or some other scripting language, I'm not saying it's impossible to do just from assembly, but it takes so long to do it if you have to read the assembly code. It is so much quicker if you have a decompiler. Now, the decompiler, people say it's cheating or whatever, but really you don't need it to tell you the exact algorithm. What you need it for is you need it to basically shrink down the all of this, like say loops and stuff like that from assembly. What it does is it'll shrink it down into some manageable code that you can actually read. So instead of it being like hundreds of lines with a bunch of loops, you can see like, oh, that's just like two nested while statements. So you guys can you can do this from the assembly too. You can trace it through and say, okay, well, this looks like a counter. Okay, this is like a loop here, but that takes a long time. So if you're going to be doing this often, I can't recommend enough to get the decompiler. So anyway, my recommendations aside, I am going to use the decompiler to go through this quicker, and I think you'll see how it makes this a little bit easier to see what's going on. All right, so we can see get host by name. This is the this is going to be the domain that we're looking at. So what we'd like to do is probably see where the domain comes from. So we can see here if the domain is null, then skip this whole thing. So let's go to the other usage and see whether that checks whether the domain is null or not. So let's jump over to the other usage. So again, this is going to be the domain. It looks like the domain comes from this function. So if we look at this, let's drill in a little bit more. Okay. I don't know what this is here. What we're seeing here is we're seeing what looks like maybe a dynamically resolved API. So I'm going to take a look at this and see. So they push global alloc and then get process address. And then, so that's going to be in EAX. And then they move EAX into this right here. Okay, so I'm going to rename this pointer to global alloc. All right, so basically what we're seeing here when we see this sort of like string getting passed to get process address and then the response being stored into a D word, we can see basically that's how import addresses are resolved. So this looks like some dynamic import address resolution here. So let's go back to our function. We will, and we're going to call this, rename this as wrap. Oops, wrap global alloc. So what I like to do, this is just my own preference. So what I like to do is anytime we have like a function that's just a direct call out to an API, I just call the function wrap, as in it like wraps the API. Even if they do a little setup before the API, I usually call them wrap underscore the API. It just keeps it a little cleaner when I'm reading the code. So we have like a global alloc here, comes into this. And this is a mem copy. Okay, so again, I'm going to recall this wrap q mem copy. All right, and so let's look at this function. So it looks like they're copying whatever's in A1 over. So let's call this name wrap. So again, even though there's like the alloc and then the copy, I'm just going to call it wrap. Now, this is like a naming convention, again, that I use just to sort of keep things straight when I'm like reading, when I'm trying to like first look at a binary. And all I'm trying to do is I'm trying to give names, slightly descriptive names to functions so that when I see them in other functions, I know I've already looked at them and I have some inkling of what they do. Again, here there's a bunch of other stuff going on, but all I care about is the fact that it's basically doing a mem copy. And we should actually rename this. So I usually rename my variables var underscore, a very Pythonic naming convention. You guys can tell I mostly write stuff in Python. But so I'm going to call it var underscore domain, just to keep it straight. Let's take a look at this buff here and see what's going on. So it looks like that's created with this function here. So it looks like there's a loop here. The reason why I paused for a minute is there's a loop here. So let's take a look at this function and see what they're doing here. Oh, I see. Okay. So this is just part of some network communication. So we're probably not on the right track here, unfortunately. So let's take a look at the other get host name. Let's see where this is called from. Actually, let's call this wrap get host by name one. And again, that's not what this is doing. This function is doing a bunch of other stuff. But and if we jump and see that there's another function, the other function, let's just name it wrap. Wait, what am I missing here? Oh, I misspelled it. Wrap, please. Wrap get hostname 2. All right. So let's pop back to the other guy. I'll fix this name. Wrap. All right, and then let's see where he's used here. Jump to xref. All right. So here we go. Looks like there is some more network setup here. Just gonna click around and see what these functions do. So if you're wondering like what am I doing? What I'm looking for is I'm looking for a function that has a loop and a bunch of constants or a bunch of like hard-coded D words. And the reason why I'm looking for that is because that's what a random number generator looks like. So that's when I'm kind of like clicking through these quickly and like I'm looking at it, I'm like, oh, okay, well this is just some network setup stuff which I don't really care about. That's why I'm kind of going over this quickly. Sorry, I should have just explained that as I was doing it. I sort of just went into auto mode. But basically what I'm doing is I'm just kind of clicking around and trying to see where this, so if we go in here, you can see that this is the domain name here. So I'm trying to see like where this domain name comes from. That's all I care about right now. I don't really care about like, that's why I'm kind of naming this like get hostname, because I don't care about the other functionality of the function. I just want to trace how the domain name is used. So it's used here in this function to how it's generated. So I just want a list of functions that are named basically based around what they're doing to the domain name. So if we scroll back, or if we go back here to this here, so we can see that this is only used, this domain name is only used once. So we're going to rename this as well, and we're going to call it wrap get hostname. So again, I don't care about what it's doing. I know it's doing some network traffic. I know it's doing like socket setup, et cetera, et cetera. I don't care. All I care about is how it works in relation to the domain name. So let's go to the XREFs for this guy. Interesting. Okay, so now we're getting somewhere. So this is, I'm gonna name this again. So we're further up on the chain. Wrap. It's a wrap, yo. Dad jokes. All right, so let's go to the XREF for this guy. And again, we just keep looking for where does this come from? Where does this come from? Where does this come from? So here we can see now we're getting somewhere. We can see that it looks like it was probably copied, or it was probably generated here because we passed by reference. So it's probably something is being set in that function. So let's take a look at that function. It's the second argument. So the second argument, name arg cp, and where are you used? All right. So again, not a whole lot going on here. Like we're checking here. Yeah. So it looks like we have an alloc. Maybe we're copying something over. Oh, okay, this is probably a copy. So here what we can see is, here's the CP that I care about. Let's take a look here. This is google.com. So if we go back to our pseudocode, you can see that's being assigned to the string. The string is being passed in here. That's the domain. So I'm just going to totally guess that this is probably some sort of like copy or like some sort of parsing of the domain and setting the actual domain into the CP. So I don't really care. Again, I don't really care about this. I might name it. Here's another naming convention. If I don't even look at the function, like I just do a pure guess at what it does. I type in maybe. So maybe copy host name or domain name. Or maybe it's a generic copy. Maybe it's just generic copy for strings. Let's see how many xrefs it has. That should tell me. Oh yeah, it's probably related to domain. If it was just a generic copy, there'd probably be a lot more references to it. Anyway, we know that we're not in the right function here. So, oops, what's going on here? Let's jump to another one of these xrefs here. Okay, it looks like the same sort of deal. Let's jump to another xref. Let's see what we got here. Looks like the same deal. How about this guy? It's a little different. Okay, so he's being passed the CP into this function. So name, and he's going to be wrap get host name, and I'm going to put the different in here. So you can see this is like a so what I'm doing here, this is kind of like a naming convention that only I use. So I wouldn't send this, like I wouldn't export an IDC and send this to another analyst. I'd want to clean these up first. This is the only reason why I'm naming these functions is because I'm tracing up where they go. Now you can do like a right click, like trace xrefs to or something, and it'll show you like the call graph, and you can see like what functions it goes through. But the reason why we don't really care about that is because we have to look at each one of the functions anyway to see what it does. So there's no real point. Like, yeah, ooh, wow, the graph looks nice, but you still have to go and look at each function. So in essence, that's what I'm doing. In essence, I'm just building the call graph the same way that IDA does it, only I'm kind of naming them. I'm giving them some sort of name that might be interesting if I have to go back. So the reason why I'm calling this diff is because it's different from the other wraps. Basically, if that makes any sense. So let's see where this guy's called. Okay, he's called in a bunch of different functions. Oh, that's interesting. So where does CP come from? Okay, so here we have that copy again, so it's probably not this function. Let's check this guy here. String. And okay, what's this function here? Okay, interesting. There's like a loop here, might be what we're looking for. And hey, all right, jackpot. Okay, so this to me, and probably to anyone who looks at it, it looks like a random number generator. It looks like, the reason why I say that is because there are a bunch of hard-coded constants here and a bunch of math that is returned by the function. It's very simple. There's not a lot of loops or anything. Remember, random number generator, the core component of it, its only job is to take in the seed or take in the iteration seed and produce one number. So it's really just one line of math with a bunch of constants. So I think this is the random number generator. So what I'm going to do is I'm going to name that maybe RNG. All right, and so now I'm going to pay closer attention to, it's used a lot. I should go back. I'm going to pay closer attention to this function here. So it looks like if that is the random number generator, it looks like whatever is being returned is being, interesting. So it looks like we're adding the offset of the lowest character in the ASCII table to whatever is being returned from the random number generator, and then we're adding it to a string here. And yeah, this definitely looks like what we want here. So this is the string. So let's see if we call this like maybe RNG, let's say like maybe RNG DGA, and let's see where that was used, where we came to it from. So if that does return the string, and then yeah, that's the DGA, that is the domain that's being passed into our get host name. So I think we found it. We're going to have to look a little bit deeper at what's going on, but to me that looks like it looks like we actually found the function. Now, like I said before I started this, there's another way to do this that might be a little bit of a shortcut. and that's to find the TLD and find the TLD string and see where it's used. So what I mean by TLD, if you don't know, that's top level domain or top layer domain. That's like .com, .org, whatever, .ru, whatever the dot is. Find that and then see if there's a string of that in the binary. So what we can do is if we pop back over to our domain list here, we can see that the TLD is .com. So it's the domain name .com. So if we look in our strings table, we can see if we can locate where, if there's a .com, if there is in the strings table, and if there is, we can see if we can locate where it's used in the code. So lucky for us, like most of the malware that I've been working with in the past like couple of years, they encrypt the strings table. But lucky for us, these guys don't, so it's going to be even easier. We don't have to decrypt the strings table first. They're already decrypted. So all we have to do is look through here and see if we can find a com or a .com. So I'm going to just alphabetize it so it's a little bit easier. There's a .com. So let's see where .com is used. Oh, hey, that looks good. That looks like looks like it's being used in the maybe RNG DGA. So let's jump to xrefs. Yeah, so it looks like it's being used in. I'm just going to flip this over to our pseudocode. Yeah, here we go. So we're actually appending stircat.com onto whatever came out of this generation thing. So now we can be pretty certain that we've located the random number generator. I know that it might have been a little difficult to follow and it was a little bit mumbly as I was trying to trace my way up the calls from from that API that's using the hostname. But that's basically, it's just a manual process that I do, and I find a lot of dead ends. The reason why it might be a little difficult is because when I'm looking at the functions, again, I told you I already kind of have in my mind what I'm looking for. I'm looking for that set of constants, that are being used with a bunch of math to return whatever's in a loop. And the output of the loop is being used as a host name. So that's why I was kind of going fast, and you might not have been able to follow each step. But if you want to take this approach is easy as well. So it's easier to follow, where you just find the TLD, and then you find where it's referenced in the code, and you see, like, is it appended to a string? If it is, where's that string coming from? So the hindrances there are that it's not always going to exist as a string. It might be built like one character at a time, or it might be encrypted, so you have to decrypt the strings table first. There's lots of things that might sort of hinder that process, which is why I tend to do the API process first. That's tends to be what I look for. But again, doing them both, like we just showed, is a surefire way to make sure that you found the actual DGA. And the fact that the .com was only used in one function, and it was the function that I'd already picked as a probable candidate for the RNG, it kind of confirms it. So now that we've located the RNG and the DGA algorithm, what we need to do is we need to sort of transpose or copy the algorithms out into Python or whatever scripting language we want to use, so that we can replicate them and generate the domains that we need. So what I'm going to do is I'm going to start with the RNG. It's a simple one-liner. So I'm just going to actually copy this out directly. And I have a notepad open over here. So I'm just going to paste this in. And I'm going to save this file in temp as dga.py. All right. So let's clean up this RNG algorithm a little bit. I'm just going to come back over here. I'm going to call it, actually return is fine. And I'm going to make this a function, I guess. RNG and A1. And there's an A2 as well. A2. And let's make that the algorithm. Okay. and then I'm going to go and see how this is actually used. So I'll just save that and pop over here. Oops. There we go. So I'll pop over here. Let's go back and see how this is used. So it looks like it's called twice. The first time we're passing a value C, or sorry, that's 12, and we're passing a value 25 into it the second time. And because the second time it looks like it's this is actually what's building the string. So we'll get to this in a minute. Let's take a look at the first one, and there's something kind of weird going on here, because here we're actually returning and we're using a variable that's being returned. Here we're not really doing anything, and so an important thing to note here is that I noticed something is wrong here with the pseudocode. And this happens a lot because a lot of the times the IDA decompiler is just making assumptions in order to generate some C code that makes sense. So a lot of the time, if the assembly is doing variable passing and registers, it's not through standard call or something like that, then you can end up missing variables or missing part of the algorithm. So the first thing I'm going to do is I'm going to jump in here. This is called maybe RNG, and I'm going to take a look at the assembly code for this. So I'll just go to it. Maybe RNG. All right, let's take a look at the graph view here. All right, it's just a one-line algorithm. Okay, so the first argument, if we look back here, is going to be, it looks like our seed because it's actually being used in the algorithm. And the second argument, it looks like it's our modifier. So because once so you can see this bracket is matching the very first bracket in the function statement. So you can see that after the math is done in this function, the final result is actually modded by the second variable that's passed in. So what that generally means is that's like the compression. I don't think that's the right mathematical term, but it's basically when you're taking a large number and then you're distributing it over a smaller subset of numbers. So like if you say like mod 9, then all possible results will fit between 0 and 9. That's basically, again, I know there's like a name, there's like a mathematical name for what you're doing when you like reduce a set of values into a smaller subset, a smaller key space or whatever you're calling it. I just can't remember the name for it, but that's basically what we're doing. So we know that the second arg is the modifier arg mod, and oh whoops, hit the wrong key. And the first argument is going to be the seed. Okay, so if we look at our assembly here, we know that well, they've already named it for us. So here we can see the seed is passed into the beginning of the algorithm. You can see there's a bunch of like the divs and multipliers and whatever, and then you can see the final result is modded by the mod argument. Now, one thing that's important to note here is that the returns. So it looks like, let's see here, EBX and EDX. So what I'm doing is I'm looking at the registers that are used to return values from this function, because I'm suspicious that the IDA pseudocode isn't correctly identifying how the variables are being passed back. So it looks like we're copying something over into EDX, EBX, and ECX. So I'd like to take a look at how those registers are used in the function that calls this. So what was that called here? Let's go back. It's called maybe RNG DGA. All right. So let's go to. All right, and indeed. So we can see that upon return here, EDX is moved into a variable and saved. So it looks like there's an extra variable that's not being caught in the pseudocode that's being moved out. So we're going to need to capture that in our in the algorithm that we copied out. So let's take a look and see if we can figure out what EDX actually is. So it's stored in this variable, and that's used down here. EBX is multiplied by the. I see. It's multiplied by the original seed value that's coming in. So if we look at what was actually passed to the RNG, we can see here's 12. That's the modifier, and here's the seed. So it looks like the seed is actually the argument being passed into maybe RNG DGA. So let's name that as arg seed. Okay, so we can see that that's the seed that's being passed in, and I think so it's actually being into EX. Yeah, it looks like it's actually being multiplied by this value that's being saved out of RNG, the value that's being passed back in the EDX register. Oh, and it's also okay, here we go. I think I know what's going on. So in the RNG, so if we go into the RNG function, they do their bit of math here. There's the seed and the mod, and they do a bit of math, and then they save one of these registers out to EDX, and when you return from this function back here, they save EDX over here. But EDX is then used, it's actually being passed into the next call to maybe RNG as the seed value. So this is the new seed. Okay, so I think what's happening here is when the random number generator returns, it's returning both the next seed value. So again, a random number generator is passed the seed, and then it iterates in a loop, right? So it iterates new values, and each time it iterates, it spits out a new random number. But it also needs to it also needs to keep track of where it is in the sequence of random numbers. So it looks like they're doing that in this case by modifying the seed and repassing the modified seed to the random number generator. So what I'm going to do is I'm going to pop over to our algorithm here, and I'm going to just fix that up a little bit to make a little bit more sense out of what's going on. So we know that the first value is the seed value. So let's replace that in our algorithm here. Seed value, and that's the seed value. And then we know the second is the modifier. Let's just call it mod. All right, so that's our mod. And we also know that the RNG is returning two values, the random number and the seed value. So let's make it so it can return both those numbers. So we're going to call this new seed, and the random number equals new seed modified by that. And let's return both. So let's return the random number and the new seed. Okay, there we go. So now our algorithm properly matches the algorithm that we see in the assembly here. Now again, if I was to switch this back over to the pseudocode, you can see we only see the one return. We only see the return of the random number here, right? Or sorry, the random number here that's added to A or 61. Lowercase a. We only see that random number being returned in the pseudocode, but we know from looking at the assembly that it's actually returning both the random number and the new seed value, which needs to be passed in. So if we look here, you can see this kind of sums it up for us. You can see here that v2 is being passed into the random number generator, and of course v2 is not referenced anywhere else here. It's not, we can't see it being returned from maybe random number generator. So you can see that this is why and we could fix this up. We could make some calling conventions up, function definitions up to make IDA kind of understand this a bit better, but there's no need to. We know how it's working from looking at the assembly, and this is actually a pretty straightforward algorithm, so there's no need to go mucking around with that. But just keep in mind that you can't rely on the pseudocode 100%. I mean, it's IDA's best guess at what's going on. So like I was saying before, it's really good for figuring out like logical, like while loops, for loops, and stuff like that. Control flow, it's really good for that at a high level, but it's not so good for like the small details. You really want to look at the assembly for those. Okay, so now that we have our random number generator algorithm sorted, we have to sort out the part that actually turns that into a string, which is this actual symbol algorithm here. So it looks like it's taking the result from the random number generator, and it's adding a, which is, if we just to explain that in case anyone's not familiar with like the ASCII table, let's look at ASCII table, please. So what I'm talking about here is basically, if we look at lowercase a, that's a hex offset of 61. And so if you were to, and of course we have the entire alphabet up to 7a or 122, 122. Basically, if you were to generate a random number within this space between 0 and 26, and you added 61 to it, you would really be generating these ASCII characters between A and Z, all lowercase. So so that's basically when I was saying before, like, oh, it looks like they're adding A to make it lowercase. That's what that algorithm is doing. So if we pop back to it, it'll make a bit more sense here in a second. We can see that basically here's the output of the random number generator plus A, and then we add it to the string. And we're doing that for some loop, which again, we can see there's something wrong with this interpretation, with this pseudocode. We can see that they are doing some sort of test, but it's not it's not working properly. So so basically what we want to do is we want to reproduce this algorithm here, and then let's look at the assembly to figure out how long the while loop goes for. So this algorithm here is quite simple. If we pop back over here, we just do a while true. I'll just do it for true for right now. And we're going to do actually, let's create our domain. Domain is blank string for now. So domain plus equals the RNG, and we don't really know, we don't know what the initial seed is. Start seed equals, and we don't know what it is yet. Actually, let's just call it a none for now. So we send in the start seed, and what is the modifier for this? It's going to be 25. All right, so that's our alphabet basically, right? Like I was saying before, I said 26, but it's actually kind of funny. It's 0 to 25, so 26. Here we go. So it's 25, and then they add into it 0x61. Where's that? Yeah, there we go. And then of course, because we're in Python, we're going to need to turn this into a char before we can append it to the string. So we're going to turn that into a char. Okay, so so this looks like the beginnings of building the domain. What we don't know is we don't know how long the while loop is for. So that while loop is actually, if you think about it, it's going to control how long the domain is. So depending on how long the while loop goes for, we're going to append characters to the domain. So wherever the while loop stops, that's the length of the domain. Okay, so let's go back and take a look at the assembly and see if we can figure out where the while loop stops. So let's go over here. We have our loop. So loop is a command that counts down the ECX register. So let's see what's, oh, okay, yeah, this is pretty straightforward. Yeah, so basically the way loop works is it decrements ECX, and whenever it gets to 0, it breaks, otherwise it loops. So it's just a fancy assembly command. So we want to figure out what's in ECX. So if we look at this, here's the missing piece. So if we look at the RNG, the first time we call the RNG, the results from it are stored in EAX, right? That's the standard return. So they add 8 to that return, and then they store, so that's 8 plus EAX, and then they store EAX and ECX. So now that loop loops for whatever 8 plus the first result from the random number generator. So let's add that in. So that looks like they call the random number generator first to determine how long the string is going to be, and then they call it again in a loop to actually build the string out. So let's replicate that in our algorithm here. So before we start all of this stuff, what we need to do is we need to call the random number generator again. And I also made a mistake here. I'll show you guys in a second. So what was the modifier here? Right, 12, OC. Where are we here? Oops. There we go. So 12 is the modifier, and again, we don't know what that start seed is. But remember, oh yeah, that's right. Here's the return. So remember, the return isn't just the random number, it's both the random number and the new seed value. So really what we should be doing is the seed starts up here. The start seed is passed to the first call to the random number generator, where we get the domain length. And then the new seed is passed to the second second call to the domain generator in the loop, where we actually build the domain. And so I also messed this up a little bit. So instead of this being instead of this looking like this, really what we need is 2 calls. We need the first call to be telling us what the new seed is and the new random number. Okay, and so we need to, because obviously for each loop, for each iteration of the loop, we need a new seed. So we need to take that out, and then we can use the random number in the domain generation. So that was a little mistake that I made before. I didn't catch it until just here. So, and we want to call this build the domain string. Okay, and the other thing that we want to do is we want to take, so this isn't a random number, or sorry, this is building up the domain length. So the domain length is, let's call it length, equals the random number that was returned from, the random number that was returned plus 8, I think. Let's go up here and check again. Yeah, so call it a random number. The return value is an EAX. EAX plus 8 is then stored in ECX. Yeah, so it's plus 8. So there's a couple of things that this kind of tells us about the domain already. So plus 8. So this tells us that the domain will never be shorter than 8 characters. So that's interesting. It also tells us that the domain is going to be all lowercase characters because, of course, we're only adjusting for the key space or like the length of the alphabet for lowercase letters in the ASCII table. And one other kind of interesting mess up here is that there are 26 characters in the alphabet, not 25. So when you mod by 25, you're going to miss the final, you're going to miss Z basically. So, so good job on whoever developed this algorithm. You're going to be, your domains aren't going to have Z in them. So, I mean, that's interesting. But from where we stand today, this looks like we've probably rebuilt our domain generation algorithm. The only thing that we're missing now is the start seed. Oh yeah, sorry. We also have to fix the while loop to for I in range 0 to domain length. There we go. So we need to build that out, and then we need to make the domain print plus com. So the domain plus, we'll add on the TLD, which is .com. Okay, so it looks like we have what we need to build the domain now. So what we need to do is we need to find the start seed. So we need to find what starts the whole generation algorithm. So before we do that, I just want to recap here and say that we've learned, in addition to the kind of funny mistake about there not being any Z in the domain, and the fact that the domain is always going to be at least 8 characters long, we've also learned that this domain is going to be composed of lowercase letters only. And once we find the seed, we can figure out how, like, we can basically generate as many domains as we need to for whatever seed is given. So let's pop back to our assembly here. I'm going to use the pseudocode view of this because, again, now we're going to start looking high level. We don't need to drill into the details anymore because we have mostly the algorithm figured out. So let's jump into our pseudocode here. So we know that this is the key. This is the start key. Start seed. And so we need to figure out where this is called from and what the start seed is. So that's going to make it easy for us. It's only called in one place. And the start seed is a hard-coded D word. All right, this is going to be easy for us. Okay, so it looks like that's our start seed. So I'm going to pop over here and place that in here. Okay, so that's our start seed, and we should be able to start generating domains now. Now, what this tells us is that for each malware sample, there is going to be a finite number of domains generated. Because the seed is a hard-coded int or a hard-coded D word, it's not going to change with the day. So it's not like a time-dependent DGA where each day has a different set of domains. Once you generate this set of domains, it's good for the sample for the rest of the lifetime of the sample. So this is actually a good one for us. It's a good one, like I said, it's a good one to practice with because it's straightforward. And once we've generated those domains, we can basically put them on the blacklist or do whatever we need to do with them. We know that they're going to be good for the lifetime of the sample. Something else to note, though, is that we still have to run this, and we need to make sure that it's correct. And the way that we do that is we compare the output from this with the with the domains that were generated in the sandbox. Now, if this was like a time-dependent DGA where the seed was, say, like the day or like a timestamp or something like that, then we need to be careful about comparing the same timestamp. But because this is a hard-coded D word, we know that the domains that we generate should match exactly the domains that were generated by the sandbox. So let's run this. I'm just going to copy this over into a Python shell, Python interpreter, and I'm going to see what the first domain is that gets printed out. So I think I have a, yeah, here, let's use this guy here. So Python, and I'm just going to paste in that code. There's a mistake somewhere. Oh, I forgot myself a full colon on the end of that. All right, let's try this again. Copy and come over here, paste it in. What do we, domain length isn't defined. Hey, you guys get to see me troubleshoot Python live. Outrageous. Okay, so we're just going to copy this over here. Try this. Try this again. All right, and let's copy the rest of the stuff over here. This should work now. Okay, there we go. That worked. All right, so let's go and see if this domain matches. So dvwt, and we got to go over to our samples here, and dvwt looks good to me. Oh, no, something's kind of messed up here. Okay, so it's pretty close, but something's wrong. So I'm gonna go and check the, let's kill this. Oops. And I'm gonna go back and I'm gonna check the assembly and see, make sure that I got the right, seed. So where is the seed used? Jump to cross references. Okay. All right, so this is, so this is where it's passed into the RNG. Okay. Now, where else is it used? Okay, so I see the return from the RNG is actually set into it, which makes sense because we're going to need to iterate that seed for the next domain that we generate. So that makes sense. But I thought I saw it used somewhere else. Yeah, it's written to somewhere else. Okay, so something is popped into it. So where's the last push? Push is this argument here. Push. And popped into, let's name this D word seed domain. All right, and so arg0 is popped into it. So let's see what arg0 is for this function here. Oh, it's another, it's another domain, or it's another seed value. Okay, that's kind of tricky. Name dword real seed value. Real start seed. All right, so let's try this seed and see if we get some better luck here. Let's pop on over. And let's try this guy here. Actually, I'll just comment this out. Or I don't even need to. I'll just reassign it. Oh, am I missing? Did I miss one of these characters or something? 1, 2, 3, 4. 1, 2, 3. Okay, let's give this a try instead. Save that up and then copy that. Let's run it again and see. Okay, that's a different OAWV. Okay. So was that other one just sort of a fluke? Hey, okay, yeah. So we got the right one. So there was kind of a trick there in that DGA where if you use the seed that it looked like that was being passed directly into the function, you would have generated the wrong set of domains. But you could see that earlier in the program, that seed was actually overwritten with another seed, sneaky, and we can see that these are actually the domains that are being generated. So that, in a nutshell, is basically how you build a DGA. So we figured out how to locate the DGA. Well, first of all, we figured out in the sandbox that there probably is a DGA by the randomness of the domain names. Then we figured out how to trace a DGA by backstepping through, by locating an API call that requires the host name or domain name, and then backstepping through the functions from where the domain name came from and looking for a function that had a bunch of constants and some math. Basically, in any function like that, we would have wanted to investigate further. So, and then we also use a trick of finding the top level domain, the TLD, so .com in this case. We found the .com string in the strings table and then located where that was actually used and what function that was used in. So that's how we traced out where the domain generation algorithm was located. And then I showed you how to copy that out, copy the algorithms out by looking at the pseudocode for the high level logic for the control flow, like the loops and stuff, and then looking at the assembly for the low level to figure out what's actually going on, if there's any like hidden registers passing stuff, if like the function call definition is wrong or whatever. So, or the function definition is wrong. So basically we took you through all those steps and now we have the Python algorithm. So next up, I'm going to clean this up a little bit to make it into a function. I will link this script in the description below the video as well, so that when you go and reverse engineer, if you want to go back and follow my steps and reverse engineer this for yourself and make sure you can follow the steps, you'll have this script to compare your notes against to make sure that you did it the right way. So as always, I hope this was informative. I know that this was a little bit more technical, a little bit more in depth, and also you'll have to forgive me. I stumbled a little bit on this one because this one's actually done completely live. So I didn't really know. I mean, I know what Ramnit is, and I knew that like basically that it's a static DGA. But I didn't know, like I had never looked at the binary before. So you have to forgive me for sort of stumbling a little bit. This is about as close to live as you get. So hopefully you like that more. I did get some requests to actually do stuff really like actually live. So I wanted to do this one without any prep just to see if like I could do it, to see what it was like. So thanks for bearing with me through some of the stumbles. I did edit out some of the parts where I was like, what is this? But pretty much all the stumbles and everything are in there. So that's kind of what it looks like. As always, like I said, keep your requests coming. The feedback I've been getting and Sean has been getting has been super positive and super awesome. It's funny, we're talking, I don't think we ever introduced ourselves. So my name is Sergey, and the bearded fella who did the doc tutorial video is Sean. We both work together to bring you these free tutorials through Open Analysis. And you can find us on Twitter. I'll put our links in the bio or in the description below. So you can always reach out to us on Twitter if you have any questions or comments. Feedback is always welcome. And like I said before, we're going to take a break. Sean is also going on vacation, so we probably won't be posting anything until the end of the month, but we will be trying to get back on schedule then. So until then, keep exposing the mechanics behind the malware and stay curious, and we'll see you in May. Bye.